The Pacific Ocean is the largest and deepest body of water on Earth, stretching across more than 60 million square miles and covering nearly a third of the planet's surface. But size alone is not what makes it significant. It is what remains unseen that defines it. Beneath its shifting surface lies a vertical world that quickly escapes human perception. Sunlight fades within the upper layers, and beyond that point, the ocean transforms into near-total darkness. Pressure rises to extremes that would crush most known structures, while temperatures drop and movement slows into an environment that feels almost disconnected from life as we understand it. Yet life exists here. From glowing deep-sea organisms to vast underwater mountain ranges and hydrothermal vent systems, the Pacific contains ecosystems that operate without sunlight, driven instead by chemical energy and geological activity. These are environments that have developed in isolation for millions of years, largely untouched and still only partially documented. At its deepest point, the Mariana Trench, the ocean descends nearly 11 kilometers below sea level. It is a space so extreme that even modern exploration has only briefly reached it, leaving most of its terrain uncharted. And this is where the uncertainty begins. Despite centuries of navigation and decades of advanced oceanography, the vast majority of the Pacific remains unexplored in any detailed sense. Entire regions have never been directly observed, and much of what is known comes from limited sampling or indirect measurement. So the question is no longer whether the Pacific is large. It is what still exists inside it, waiting to be discovered. It's bigger than all land combined. The Pacific Ocean is not just vast, it is dominant on a planetary scale. Covering more than 60 million square miles, it stretches across an area so large that all of Earth's continents could fit within its boundaries and still leave vast expanses of open water. From space, it defines an entire hemisphere of the planet. A continuous body of water extending from the Arctic to the Southern Ocean, and from Asia and Australia to the Americas, it occupies nearly one-third of Earth's total surface area. But what makes this scale significant is not just size, it is separation. Because within its boundaries lies an entire planetary divide, thousands of islands, deep ocean trenches, volcanic arcs, and vast empty regions where land is absent for thousands of kilometers at a time. The Mariana Trench plunges deeper than any point on Earth, while surrounding zones remain largely unexplored, mapped only in fragments. The implication is simple, but unsettling. We do not just live beside the Pacific Ocean. We exist on a planet where one continuous body of water dominates the surface so completely that it reshapes climate, geography, and even the boundaries of human understanding itself. And compared to it, land is only a fraction of the story. The deepest place on Earth isn't on land. The Mariana Trench lies hidden in the western Pacific Ocean, so deep that it marks the lowest known point on Earth's surface. At its deepest section, known as Challenger Deep, the seafloor plunges to nearly 11,000 meters below sea level, about 36,000 feet into the ocean's abyss. To put that into perspective, Mount Everest could be placed inside it and still remain completely submerged, with kilometers of water above its peak. But depth here is not just a measurement, it is a condition of extremes. Beyond 1,000 meters, sunlight disappears entirely. Pressure increases to levels exceeding 1,000 times what we experience at sea level, creating an environment where metal structures must be specially engineered just to survive the descent. And yet, even here, life exists. Organisms adapted to crushing pressure and total darkness inhabit a world that remains largely unmapped and only briefly explored by human missions. The implication is unsettling. If one of Earth's most extreme environments is still only partially understood, then the deepest point in the ocean is not just a location, it is a reminder of how much of our own planet remains out of reach, hidden beneath kilometers of silent, unexplored water. An ocean that's shrinking. The Pacific Ocean looks permanent, immense, unchanging, almost infinite from the surface. But beneath that calm exterior, the structure holding it together is not static. It is slowly shifting. The Pacific Plate, the massive tectonic slab that underlies most of the ocean floor, is being gradually reduced at its edges. Around nearly its entire boundary, it is meeting other plates in deep ocean trenches where older crust is forced downward into the Earth's mantle, a process known as subduction. This is not a sudden collapse. It is a geological cycle measured in millions of years. New crust forms at mid-ocean ridges, while older crust is continuously consumed at subduction zones. But in the Pacific, the balance is uneven, destruction dominates creation. Ringed by this network of converging boundaries, often called the Ring of Fire, the Pacific plate is being pulled inward from multiple directions, its edges recycled back into the planet's interior. And the implication is subtle, but profound. What we see as the world's largest ocean is not fixed in size. It is part of a dynamic system, one that is slowly reshaping itself in real time, where even oceans can contract, shift, and eventually transform entirely over geological history. The Pacific is not just vast. It is changing. The most dangerous region on Earth. Encircling the Pacific Ocean is a massive geological boundary known as the Ring of Fire, a continuous arc of tectonic activity where the Earth's crust is in constant motion, breaking, colliding, and reforming along deep underwater faults. This is not a stable zone. It is a pressure system stretching for roughly 40,000 kilometers, where multiple tectonic plates meet and interact beneath the surface. Along these boundaries, one plate is often forced beneath another in a process called subduction, generating intense seismic and volcanic activity. The result is extreme concentration. Around 75% of the world's active volcanoes are located within this belt, and it also produces roughly 90% of all earthquakes on the planet. Here, entire landscapes are shaped by sudden release, volcanic eruptions, deep ocean trenches, and powerful earthquakes that can occur without warning, across thousands of kilometers of connected fault lines. But the real implication is not just frequency. It is unpredictability at scale. Because the same forces that build volcanic islands also trigger massive seismic events. The same boundaries that create new land are also responsible for some of the most destructive natural disasters in recorded history. The Ring of Fire is not just a region of instability. It is a reminder that beneath the surface of the Pacific, the planet is still actively under construction, constantly shifting, collapsing, and rebuilding itself in real time. It was named for calm waters. When Ferdinand Magellan's expedition entered the vast ocean beyond South America in 1520, the crew had just survived months of violent storms and unpredictable seas in the southern Atlantic and the Strait of Magellan. What they encountered next was strikingly different, open waters that appeared unusually calm and stable compared to what they had just endured. Because of this contrast, Magellan described the ocean as Mar Pacifico, meaning peaceful sea. The name would later evolve into what we now call the Pacific Ocean. Oceanservice.noaa.gov. Britannica.com. But the label only captured a moment, not the reality. Because the same ocean that seemed calm to early European navigators is also home to some of the most violent weather systems on Earth. Typhoons form across its warm equatorial waters, powerful storms build across thousands of kilometers, and its edges are constantly reshaped by earthquakes and volcanic activity along the Pacific Ring of Fire. The implication is clear. The name Pacific was never a description of its true nature, it was a first impression. A brief moment of calm written into history, masking an ocean that is anything but peaceful. And beneath that name lies a system that is vast, active, and still far beyond full understanding. Navigation without maps. Across thousands of years and millions of square kilometers of open ocean, Polynesian voyagers crossed the Pacific without compasses, charts, or modern instruments, yet they still reached islands separated by vast, empty stretches of water. What made this possible was not luck, but a highly developed system of environmental reading. Navigators tracked the night sky, memorizing star paths and using the rising and setting positions of constellations as directional guides. By day or under cloud cover, they shifted to other signals, wave patterns moving across the ocean surface, wind direction, and subtle changes in currents that indicated proximity to land. But navigation didn't stop there. Bird behavior became a living indicator of distance from shore, with certain species consistently flying between land and sea at predictable ranges. Cloud formations and reflections on the water also revealed hidden islands long before they were visible on the horizon. Together, these cues formed a layered system of navigation, constantly cross-checked, memorized, and passed down through generations of trained wayfinders. The implication is striking. Long before modern mapping, humans were already reading the planet itself as a network of signals, turning an apparently endless ocean into a navigable world defined not by instruments, but by observation, memory, and deep environmental knowledge. And in that silence across the Pacific, direction was never missing. Only learned. A battlefield the size of continents. During World War II, the Pacific Ocean became one of the largest and most complex theaters of the global conflict, spanning thousands of islands, vast open waters, and multiple continents connected by war. This was not a single front, but a multidimensional war zone stretching across East Asia, Southeast Asia, and the Pacific Islands, where the United States and Allied forces clashed with Imperial Japan in a continuous struggle for control of territory, supply routes, and strategic naval positions. The conflict unfolded across environments unlike any other theater of war. Battles took place at sea in carrier engagements beyond visual range, in the air through massive bombing campaigns, and on land in brutal island invasions where terrain itself became a defensive weapon. What made the Pacific unique was its scale and fragmentation. Entire campaigns were fought over isolated islands separated by hundreds or thousands of kilometers of ocean, forcing both sides into a war of logistics, naval power, and rapid island-to-island strategy. As the war progressed, momentum gradually shifted. Early Japanese advances were halted, then reversed through coordinated Allied offensives that pushed across the Central and Southwest Pacific toward Japan itself. The implication is clear. In the Pacific, victory was not determined by a single battlefield, but by control of an entire ocean system, where distance, supply, and endurance mattered as much as firepower. And in that vast space, the outcome of the war would reshape the entire balance of the world. Strategy across islands. In the Pacific War of World War II, the Allies developed a military approach that reshaped the entire structure of the conflict, known as the island-hopping strategy. Instead of engaging every Japanese-held position, Allied forces selectively targeted key islands while bypassing heavily fortified strongpoints. These isolated garrisons were effectively cut off from reinforcements and supplies, left to weaken over time while the main advance continued toward Japan. The core idea was operational efficiency under extreme scale. The Pacific was not a single battlefield, but a vast network of islands separated by thousands of kilometers of ocean. Capturing every position would have meant staggering losses and delays. Instead, planners focused on islands that could function as forward airfields, naval bases, and staging points for the next phase of attack. Step by step, this created a moving frontline: Guadalcanal, the Marshall Islands, the Marianas, each one bringing Allied forces closer to Japan while tightening control of air and sea routes across the region. The result was not just territorial gain, but strategic isolation. Japanese forces left behind on bypassed islands were gradually cut off from supply lines, reducing their ability to influence the wider war. The implication is clear. In the Pacific, victory was not achieved through direct confrontation everywhere, but through precision. Through choosing where to fight, and where to let isolation do the work of war itself. Mountains you'll never see. Across the Pacific Ocean floor lies a hidden landscape that rivals anything on land, an entire world of mountains that never break the surface. These are seamounts, underwater volcanoes that rise thousands of meters from the seafloor but remain completely submerged, invisible beneath kilometers of water. Most are remnants of ancient volcanic activity, formed where magma once pushed through Earth's crust, building peaks that never reached air. And they are not rare. Scientists estimate there are over 100,000 seamounts across the world's oceans, with the majority concentrated in the Pacific Basin. Yet despite their abundance, less than 1% have ever been explored in detail. Some rise so dramatically that they rival major mountain ranges on land. Others stretch across vast underwater chains, forming submerged ridges that shape ocean currents, ecosystems, and even migration routes for marine life. But their importance goes beyond geography. These hidden peaks act as biological hotspots, disrupting deep-sea currents, pulling nutrient-rich water upward, and creating isolated environments where unique species evolve in darkness and pressure. And this leads to the deeper implication. What we call the ocean floor is not empty or flat, it is a vast, uncharted mountain system, stretching across a planet we still haven't fully mapped. Beneath the Pacific, entire ranges exist that no human has ever seen directly. Only inferred, measured, and slowly revealed. And most of them are still waiting in the dark. It controls global weather. Across the surface of the Pacific Ocean, there is a pattern of change so powerful it does not stay local, it spreads across the entire planet. This is El Niño, a climate phenomenon that begins with a shift in ocean temperatures in the central and eastern Pacific, where surface waters become unusually warm. That change might seem regional at first, but it triggers a chain reaction between the ocean and atmosphere that alters wind systems, pressure patterns, and rainfall far beyond the Pacific Basin. As warm water spreads and trade winds weaken, the normal balance of heat across the Pacific is disrupted. Moisture shifts eastward, storms form in new regions, and weather systems that usually remain stable begin to reorganize on a global scale. What follows is not a single predictable outcome, but a worldwide atmospheric response. Some regions face intense rainfall and flooding, others experience drought, and storm tracks across oceans and continents begin to shift in ways that can reshape entire seasons. El Niño does not just influence weather, it reorganizes it. It is part of a larger climate system that connects the Pacific to nearly every continent through shifts in heat, wind, and ocean circulation. And the implication is striking. A single region of ocean, remote, vast, and seemingly isolated, can quietly influence the behavior of storms, harvests, and temperatures across the entire planet. The Pacific does not just contain weather patterns. It helps decide them. Life that glows in the dark. Deep beneath the surface of the Pacific Ocean, where sunlight never reaches and pressure crushes everything familiar, the darkness is not empty. It is alive. Across these depths, countless organisms produce their own light through a process called bioluminescence, a chemical reaction inside their bodies that generates visible glow without heat or external energy. From drifting plankton to deep-sea fish and squid, this living light appears in flashes, pulses, and waves, sometimes as signals, sometimes as traps, sometimes as defense. In the ocean's mid to deep zones, it is so common that the majority of animals are capable of producing light in some form. In the total darkness of the deep sea, bioluminescence becomes more than a trait, it becomes a language. Some species use it to attract prey with glowing lures. Others release bursts of light to confuse predators or communicate in the void where sound and sight behave differently than at the surface. But the deeper implication is what makes it extraordinary. This is not just life surviving in darkness. It is life actively shaping its own light, turning the absence of sunlight into an entirely different kind of ecosystem, where visibility itself is created from within. And in the deepest parts of the Pacific, the ocean is not just dark. It is glowing with life that only exists because the light is gone. Pressure beyond imagination. Deep beneath the Pacific Ocean, in places like the Mariana Trench, conditions reach an extreme that is almost impossible to comprehend from the surface. As depth increases, so does pressure, steadily, relentlessly. For every 10 meters you descend, the force of the water above adds another atmosphere of pressure. By the time you reach the deepest ocean trenches, that weight becomes more than 1,000 times the pressure at sea level. At these depths, every square centimeter is subjected to an enormous, constant force, equivalent to thousands of kilograms pressing down at once. Even materials that feel solid on land behave differently under these conditions, where compression becomes a defining feature of the environment rather than an exception. Yet this pressure is not a sudden wall, it is a gradient, increasing with every meter of descent. It reshapes physics as we know it, gases compress, biological structures adapt, and even life itself evolves specialized forms capable of surviving where most familiar organisms would fail instantly. And the implication is direct. The deepest parts of the ocean are not just dark or remote, they exist under conditions so extreme that they redefine the limits of matter, biology, and exploration itself. A world where pressure is not a factor, but the defining reality. Most of it is still unknown. The ocean covers over 70% of Earth's surface, but when it comes to what lies beneath, our understanding is still surprisingly limited. Despite modern satellites and sonar technology, only about 20% of the ocean floor has been mapped in detail, leaving the vast majority still incomplete or poorly resolved. In fact, most of the deep seafloor remains unobserved at high resolution, making it one of the least explored environments on the planet. That means entire mountain ranges, trenches, and underwater landscapes exist in a state we've never directly seen or fully charted, only inferred through indirect measurements and partial scans. And the deeper we go, the more extreme the limitations become. High pressure, total darkness, and sheer distance make direct exploration rare and technically difficult, meaning even advanced mapping systems leave large gaps in detail. The implication is unsettling in its simplicity. We often think of Earth as a fully known world, but beneath the waves, most of the terrain is still effectively unvisited, unobserved, and unconfirmed. And what we don't see is still most of the planet. Strange sounds from below. Deep beneath the surface of the world's oceans, where sunlight never reaches and pressure reshapes everything familiar, scientists have recorded acoustic signals that don't always have immediate explanations. Using hydrophones, underwater listening systems, researchers have detected a wide range of deep ocean sounds, some linked to shifting ice, underwater volcanic activity, and migrating marine life, while others initially defy classification when first recorded in remote regions of the Pacific. One of the most famous examples is a powerful low-frequency signal known as the bloop, recorded in 1997 across vast distances in the Pacific Ocean. It was so intense that multiple hydrophone arrays picked it up thousands of kilometers apart, sparking years of debate about its origin. Over time, many of these mystery signals have been traced back to natural sources, icebergs cracking, volcanic activity, or marine animals communicating across extreme distances. But the deeper implication is what makes them compelling. The ocean is not silent. It is constantly active, filled with layers of sound traveling through pressure, temperature, and distance in ways we are still learning to interpret. Even today, new recordings continue to challenge early assumptions about what is natural, what is biological, and what is still not fully understood. And so the question remains: how much of what we hear from the deep ocean is already explained, and how much is still waiting for context beneath the noise? Hidden structures? Across the ocean floor, sonar scans have revealed formations that, at first glance, appear unusually precise. Sharp lines, geometric patterns, and symmetrical ridges occasionally emerge from mapping data deep beneath the Pacific, sparking curiosity and speculation. But when examined closely through geological study, most of these features are explained by natural processes. Tectonic movement, volcanic activity, sediment layering, and long-term erosion all work together to shape the seafloor in complex ways. Over millions of years, shifting plates can fracture the crust into linear faults, while underwater volcanic eruptions build structured ridges and plateau-like formations. These processes can create patterns that seem artificial when seen in limited or low-resolution data. Modern high-resolution mapping has helped clarify many of these anomalies, showing that what once appeared constructed is typically the result of pressure, heat, and movement acting over geological time. Yet the initial impression remains powerful. Because the ocean floor is not smooth or simple, it is fractured, layered, and constantly reshaped. And when only fragments of that vast landscape are seen at a time, the mind naturally tries to find order in what looks unfamiliar. The implication is subtle but important. The deep ocean does not hide man-made structures, but it does create natural ones so complex that they can briefly resemble them, reminding us how little of the seafloor we've actually seen in full clarity. And how easily the unknown can feel designed. Gigantic deep-sea life. In the darkest zones of the ocean, where pressure is extreme and food is scarce, life does not always follow the rules we expect on land. Here, a phenomenon known as deep-sea gigantism appears, where certain species grow significantly larger than their shallow-water relatives. One of the most striking examples is the giant squid, a deep-ocean predator that can reach lengths of over 10 meters and remains one of the most elusive creatures ever documented. This pattern is not limited to squid. Deep-sea isopods, amphipods, and other crustaceans have been recorded at sizes far exceeding their surface-dwelling counterparts, adapted to survive in cold, high-pressure environments where energy is scarce and biological efficiency becomes critical. Scientists link this growth pattern to several possible factors: slower metabolisms, long lifespans, reduced predation pressure, and environmental conditions that favor energy storage and structural efficiency at depth. But the implication goes further than size alone. Because in the deep ocean, evolution does not simply scale life down to survive pressure and darkness, it sometimes scales it up, producing organisms that challenge expectations of how biology should behave. And in that silence beneath the surface, some of the largest creatures on Earth are still moving, unseen, and only rarely encountered. A floating pollution zone. In the northern Pacific Ocean, ocean currents converge into a slow-moving system known as the North Pacific Subtropical Gyre, a vast circular flow that gradually traps floating debris within its circulation. Inside this system lies what is commonly called the Great Pacific Garbage Patch, a region where plastic waste accumulates over time, broken down by sunlight and wave action into smaller fragments rather than forming a single solid island of trash. Studies estimate it spans an area larger than many countries, with concentrations of plastic increasing across both surface waters and deeper layers. What makes it difficult to visualize is its form. It is not a visible landmass, but a dispersed field, microplastics, fishing gear, and degraded fragments suspended within the water column and spread across a shifting oceanic system. Much of this debris originates from land-based sources and maritime activity, carried into the Pacific through rivers, wind, and shipping routes before becoming trapped in circulating currents that can hold materials for years or even decades. The implication is subtle but significant. This is not a single location of pollution, it is a dynamic accumulation zone, formed by the same oceanic forces that govern currents and climate patterns. And it exists not as a fixed object on a map, but as a constantly moving reflection of human impact across one of the largest systems on Earth. Oceans under pressure. Across the Pacific, one of the most productive marine systems on Earth is showing signs of strain, not from a single event, but from sustained, long-term extraction. For decades, industrial-scale fishing has targeted key species across open waters and coastal zones, including tuna, sharks, and other high-value fish populations that form the foundation of marine food chains. As demand has increased, so has the scale and efficiency of fishing operations, using advanced sonar tracking, large fleets, and deep-water net systems to locate and harvest fish across vast distances. The result is a measurable decline in several Pacific fish stocks, with some populations reduced to a fraction of their historical levels in heavily fished regions. Marine ecosystems that once maintained natural balance through predator-prey cycles are now experiencing disruption in those relationships, affecting not just target species, but entire ecological networks. Because in the ocean, nothing exists in isolation. When top predators decline, smaller species can increase or collapse unpredictably. Coral reef systems, open water ecosystems, and migratory routes all adjust in response to shifting population structures. The implication is clear. Overfishing is not a localized issue, it is a system-wide pressure applied across one of the largest and most interconnected environments on Earth. And in the Pacific, that pressure is still ongoing, shaping the balance of life beneath the surface in ways that are not always immediately visible, but increasingly difficult to ignore. Warming waters. Across the Pacific Ocean, a slow but persistent shift is underway, one that is not visible on the surface in a single moment, but becomes clear across decades of measurement. Ocean temperatures are rising. The Pacific absorbs vast amounts of Earth's excess heat, and as this energy accumulates, it alters the physical conditions of the marine environment, changing currents, stratifying water layers, and reducing the stability of ecosystems that depend on narrow temperature ranges. Coral reefs, often described as some of the most diverse ecosystems in the ocean, are particularly sensitive. Even slight increases in temperature can trigger coral bleaching, where symbiotic organisms are expelled, leaving reef structures weakened and more vulnerable to collapse. But the impact extends beyond reefs. Fish migration patterns are shifting as species move toward cooler waters. Food chains are adjusting, with predators and prey relocating at different speeds. Entire ecosystems are being reorganized in response to changing thermal conditions. And the deeper implication is structural. The ocean is not just responding to warming, it is actively redistributing it, carrying heat across basins and influencing atmospheric systems that reach far beyond the Pacific itself. So what appears as a gradual temperature change is, in reality, a large-scale reconfiguration of marine life and climate systems. And it is still unfolding. Coral collapse. Across the Pacific Ocean, coral reefs, often described as the rainforests of the sea, are undergoing one of the most widespread environmental stresses ever recorded. The cause is coral bleaching, a process triggered primarily by rising ocean temperatures. When waters become too warm, corals expel the microscopic algae living inside their tissues. These algae provide both color and essential nutrients. Without them, the coral turns white, and enters a state of severe stress. In recent years, these events have intensified. Large-scale marine heat waves are now causing bleaching across entire reef systems rather than isolated areas, leaving ecosystems exposed over vast regions of the Pacific. And the scale is global. Since the early 1980s, coral bleaching events have increased in both frequency and intensity, with some of the most severe episodes affecting reefs across the Pacific, Indian, and Atlantic Oceans simultaneously. Recent assessments estimate that a large proportion of the world's coral reefs have already been exposed to bleaching-level heat stress during the most recent global events, pushing ecosystems beyond their natural recovery windows in many regions. The implication is stark. Coral reefs are not just changing, they are being pushed toward collapse in multiple regions at once, affecting biodiversity, fisheries, and coastal protection systems that depend on them. And in the Pacific, where many of these reefs are concentrated, the transformation is still unfolding, quietly, beneath warming water that continues to reshape one of Earth's most fragile ecosystems. The more we explore the Pacific, the more we realize how limited our understanding truly is. Each expedition, each deep-sea mapping, and each new discovery doesn't complete the picture, it expands it, revealing how much of this vast ocean still remains beyond reach. What lies beneath is not a fully known world, but an unfinished one. Hidden landscapes, extreme environments, and life forms adapted to conditions we are only beginning to comprehend continue to emerge from the darkness, suggesting that the deepest parts of the Pacific are still holding back more than they reveal. And perhaps that is the real conclusion. That even now, after centuries of exploration, the ocean has not given up its full story. Thank you for watching this video. If you enjoyed it, don't forget to like, subscribe, and share it with others. Your support helps us continue creating more documentary-style content like this, uncovering the stories, places, and mysteries that still shape our world.